We'll, we'll start, and more people will probably filter in as we get started. Okay, so last class we talked about polynomials. So here's a polynomial. This is the variable. So think of it as you can put any value in, and then you can evaluate the polynomial by filling in those values. D here is the degree. This is called a term. This is called a coefficient. Everything we'll look at, these numbers will be between 0 and q minus 1. Okay, so that applies to the variables. So the variables will be in zq, which is just a fancy way of saying the integers from 0 to q minus 1, or the integers mod q. And same with the coefficients. Okay, so everything will be integers, no decimals. Nothing will ever get bigger than q. The way that we'll enforce things staying in zq is we'll mod it by q at the end. And you can do that at any time. So if you have some coefficients that are getting a little big, you can mod q, or you can wait till the end. It doesn't matter. When you apply the modulus, it always works. Okay, any questions about the setup here? Okay. All right, then I want to talk about arithmetic for polynomials. So let's do a simple example. We'll define two polynomials. We'll call it P1 and P2. And I could fill in real numbers. I'll just leave it as coefficients. Sorry, I already. Well. And I'll just put a dash here to denote that it's a different number. So this term you can ignore. It's just to the power of 0, which is 1. But I started writing it that way so that you could see the pattern. Okay, what's the degree of these two polynomials? 2. So it sort of represents a parabola, if you want. But because we're doing mod q, by the way, if you try and graph these and visualize them, they're not going to look like a straight line or a parabola, because it'll have like segments of it, but then once you mod q, it's going to like screw everything up. So it's going to look visually different, but you can, to visualize it in your head, you don't have to think about the fact that it's mod q. You can just visualize them over all the real numbers, and then, yeah, okay. Okay, so what can we do with polynomials? So there's 5 things that we can do. 4 of which are relevant to what we want to do, and one of them that isn't so relevant, but I'll maybe say a few words about it. So it's just add, subtract, multiply, divide. And then there's something called composition, where you could do P1 of P2 of the variable. But we don't need that for this course. Yeah, so composition would be like you take P1 of P2 of a number. So let me fill it in like with a 5. So you'd first evaluate P2 at 5. You would get the answer, say it's 7, and then you would evaluate P1 at 7, kind of thing. Yeah. So this is sometimes used for, I don't know, permutation, shuffling polynomials and things, but yeah. Okay, so first we'll talk about addition. Okay, how do we add these, if we add these polynomials together, what do we get as a result? Just look, eyeballing it, you should be able to tell me the answer. So we're going to get a polynomial. So that's first. What's the degree of the polynomial that we'll get? Same. And what will the coefficients do? Okay, so it'll be the addition of the mod q. Okay, so it will be C0 plus C0 will be the new first coefficient. And then you have C1 plus C1 prime will be the new second coefficient. And then C2 plus C2 prime will be the next coefficient. Degree is still 2. Okay. And then visually, if we want to visualize it, I'll draw something more than a degree 2, but again, I won't draw the mod q, but like say we have like a polynomial that looks like this, and we have another one that looks like this. The addition of the two is the sum at every point. Okay, so let's say I go to this point, whatever this value is plus whatever this value is, that's going to be the value on the new polynomial. Okay. All right. So in other words, yeah, okay, I'll just leave it at that. Okay, questions about adding two polynomials together? Great. Subtraction. I'm not always writing it, but it might be worth just noting mod q here. So subtraction will work exactly the same as addition. It's just that you have a minus sign instead of a plus sign. If you want to get technical about it, when you work mod q, you don't really have subtraction anyway, because C0 minus C0 prime is the same as C0 plus q minus C0 prime. And since q is the biggest number, then this will be a positive number. So every subtraction is actually an addition. It's just an addition of a really big number. So, yeah. So it would be q minus C0, but, sorry, here, yes, yeah, thank you. Okay, degree, still 2. And the picture is the same. If you have P1, you have P2. Then at any point, the subtraction of the two will be the end result. So let's say we do P1 minus P2, so this will be kind of negative, and then it will kind of go positive, something like that. Exactly, yeah. So when I drew this, I'm not drawing this mod q. So these diagrams are not mod q. They're just to visualize. But when you make it mod q, it'll get very disjointed. So it'll look actually just kind of like a bunch of points, like you can't even really draw. It doesn't really make sense to even draw a line through it. But Yeah, it's just going to look like a cluster of points. Yeah. I'll have pictures of it later, like what it looks like. Yeah. Okay, multiplication. Okay, so let me draw out the full thing first. Okay, will multiplication work the same where just the coefficients multiply together? Yes, no, what do you think? So will the, so here, when I added two polynomials, their coefficients just added. Here I subtracted them, their coefficients just subtracted. If I multiply two polynomials, will their coefficients just multiply? Okay, so we have to do a full multiplication. So we have to multiply this by every term here. We have to multiply this by every term here, and this by every term here, okay? So it's not going to be as simple as the multiplications, okay? So we're going to get C0 times C0 prime. Then we'll get C0 times C1 prime box. And then we'll get C0 times C2 prime box squared. Then I'll do this term next. So we'll get C1 box times C0 prime. I'll put that out in front. I'll get C1 prime box squared. And then I'm multiplying this by the third term. So I'll get C1 C2 prime box to the 3. And then I'll do this last one. So I have C2 times C0 prime box squared plus C2 C1 prime box cubed plus C2 C2 prime box to the 4. Okay, so I do the long multiplication when I multiply two polynomials together. All right, what happens to the degree of the polynomial? Is it the same? So if I have 2 degree 2 polynomials, I multiply them together, do I get a degree 2 polynomial? I get degree 4. Okay, so why is that? It's because 2 times 2 is 4. Okay, so whatever the degree here, for this example, the degree is 4. But in general, it's going to be the degree of P1 times the degree of P2. Okay, so their degrees will multiply together. Sorry, they will add together, my mistake. It's confusing because 2 plus 2 is 4 and 2 times 2 is 4. What you'll get is the sum of the degrees of the two. Because when you multiply these together, the biggest term will be at the end, and then when you multiply them together, the exponents will add. Okay, so multiplication is going to blow the degree of your polynomial up. So that's one thing to keep in mind. Now, visually, what does it look like? Visually, it's actually the same. So if you have P1 and you have, say, P2, then P3 at any point is going to be the product of what it is at P1 times what it is at P2. Okay? So you'll get something up here. Okay? So if you think about coefficients, you have like a long multiplication. But if you think about the points on the polynomial, they do just multiply together. Okay? So P1 times P2 is just, it's all the points on P1, whatever their values are, multiplied by all the points on P2, whatever their values are, and that gives you P3. Okay, so it's clean if you think about it in terms of the points, not so clean if you think about it in terms of coefficients. There is an alternative notion of multiplying two polynomials. We won't use it, but you see it sometimes in SNARKs, so I'll just put it as a note. I'll denote the operation as a star. So this isn't, it's not multiplication as we're defining it. It's a special kind of multiplication. And the name of it is Hammondard product. And it's kind of like a dot product. If you remember like the difference between dot products and cross products. But in this case, the coefficients just multiply. So it's just C0 times C0 prime plus C1 times C1 prime plus C2 times C2 prime squared. Okay, so you could define multiplication that way where just the coefficients multiply together. But we don't know, there's not good algorithms for computing this in the kind of setting that we're going to use, where we're going to commit to some polynomials and it's just not going to be like, it's not going to be easy to do this kind of thing. So this is just a side note, it's not what we're doing. Okay, but you might see that term, and so now you know what it is. Okay, so we're going to ignore this for this class. Okay, so multiplication, it's not as simple as just multiplying the coefficients together. We have to do a long multiplication, so it's a little complicated. And the degree is going to blow up, and it's going to be the sum of the two degrees. Okay? Okay, questions about multiplying? And most importantly, the points just multiply. So if you think of a polynomial as a collection of points, if you know the points of two polynomials at a bunch of different x values, or different coordinates, then you can compute the multiplication of P3 just by multiplying them together, okay? But because the degree blows up, you wouldn't be able to reconstruct the full polynomial at P3 because you wouldn't have enough points to interpolate because you need more now because the degree's bigger. Just forget about that, it's a small technicality. Okay, let's talk about division. The other thing, I didn't say it explicitly, but maybe I should say it because it's going to change. P1 plus P2 is a polynomial, okay? I mean, it's obvious, but if you look at it, it is a polynomial. If you subtract two polynomials, you do end up with a polynomial. And if you multiply two polynomials together, whether it's this way or this way, the result is a polynomial. Okay, so you're not going to like leave, if you want to keep a bunch of polynomials, you start adding them and subtracting them and multiplying them, you're not going to end up with something that's not a polynomial. Okay, you're always, the degree might change on you, but other than that, you're going to end up. Okay, that's not going to be true of division. Okay, so if we think of P1, divided by P2, okay, so the first thing is we don't have division mod Q. Okay, so what we really mean here is P1 times the inverse of P2. Okay, we're not going to use this so much. We're actually we're almost never going to divide polynomials, or we will never divide two polynomials unless if they have a certain feature which makes division very clean. And because of that, we're not going to have to actually go through really the mechanics of multiplying, but of doing this so much. But okay, so P1 divided by P2 mod Q. First off, is this a polynomial? Does it always result in a polynomial? And the answer is no. Okay, so there could be P1s and P2s that are not divisible by each other. Okay, they're not actually going to divide. Okay, so when we divide them, what we're going to get is one of two things. We're either going to get a polynomial, or we're going to get something that's kind of like a polynomial over a polynomial. The fancy term for that is a rational function. And it's just something, it's sort of like you have some polynomial terms on top, and then you have some polynomial terms on the bottom, and you can't reduce it any further, okay? Yeah, okay. The name here?
No, on top, inside the box.
This? Hamadard. Try and write clear. Yeah. Hamadard. Which is a person, I think, a mathematician. Okay, so division's not necessarily going to work. We either get a polynomial or we get a rational function. When do we get a polynomial? And when do we get a rational function? We get a polynomial when it evenly divides. So when the polynomial underneath evenly divides the polynomial on top. And the best way of thinking of what evenly divide is last class we talked about being able to represent polynomials different ways. Let's see if I can find it. Oh yeah, sorry, so it's in this diagram here. So we said, you can put it in coefficient form. I can give you a bunch of points on the polynomial, you could interpolate it. Or I could give you a set of roots of polynomials. And if you have the roots of the polynomial equation looks like this. So it's just in root form, okay? So going back to this, if we think of P1 and P2 in root form, okay? So let's say that P1 in root form looks like this minus R1. I'm sort of regretting not giving myself more space here, so let me move this over. And P2 we can put into root form. It doesn't necessarily have the same roots, so I'll just denote the roots like this. And can we put it in root form? That's not even guaranteed. Okay, so remember, you can't even always factor a polynomial. Okay, so I'm assuming that I can actually factor it. And then assuming that I can factor it, I have these roots, okay? Then the division of the two is going to look like just the top over the bottom. When will these two evenly divide? When will we have an even division between these two? If we have an even division, what it means is that these are going to have to cancel out, right? So, for example, like say this term cancels out with this term, that kind of thing, okay? Let's say that this term cancels out with this term. That means the root is the same. So R3 equals root over -1, okay? So this will we'll get an even division when the denominators, let me put all the denominators' roots are roots of the numerator. Okay, so whatever's on bottom, it's going to have a set of roots. If the top thing has the exact same roots, it might have more than that. Okay, so it might be a bigger degree polynomial, but if it has exactly the same roots, or it has at least all of these roots and then maybe some other roots as well, then it's going to be an even division. Then the result will be a polynomial. Okay, this division will result in a polynomial. And otherwise, we won't be able to divide it. So we'll end up with a rational function. Okay, a rational function means that you're going to have some terms on the bottom and they're not going to cancel out with anything on top. And so that's not a polynomial anymore. It's not in the form of a polynomial. So it's something, it's an almost polynomial, but it's not a polynomial. So we just call it a general rational function, okay? All right, now what are we going to use of this division? Basically what we're going to do is, eventually I'm going to prove to you that a polynomial has certain roots. Okay, so I want to prove to you that it has roots at certain points. And the way I'm going to do it is I'm just going to construct what should be the division of these two polynomials. So we call it a quotient. So the quotient would be this polynomial divided by this polynomial. I'm going to tell you something about the quotient, and I'm going to convince you it's a polynomial, not a rational function. And so by convincing you that I have a quotient polynomial and it's actually a polynomial, then I've convinced you that all the roots in the bottom thing are also roots in the top thing. Okay, so that doesn't make a lot of sense to you now, but that's sort of how we're going to use this fact. We're not just going to go around dividing polynomials for fun. Okay, we're almost never going to divide polynomials, and when we divide them, we're always dividing it by a specific set of roots, and we're only doing the division to just demonstrate that those roots exist in the top polynomial. Okay, what happens to the degree of the polynomial? So if it evenly divides and we get a polynomial, then the degree is going to go down. Okay, so it's going to go down by basically all the roots that are in the degree of 2. So it's going to be the degree of P1 minus the degree of P2. We won't use that fact, but I'll put it in for completeness because we were talking about the degree for all the rest. Okay, so let me write kind of out the fact that we are going to use for this. So P2 divides P1 if and only if all the roots of P2 are also roots of P1. And in math form, I'll just write that P1 over P2. I'll just write it like this. Equals something, we'll call it Q. And this will be a polynomial. Okay, so if this division is even, then this will be a polynomial. It's not going to be a rational function. And just in terms of terminology, this is the numerator. This is the denominator. We call this the quotient. Okay. So you'll see like a term, people will talk about quotient polynomials, and it always is going to come back to this thing, this fact later. But something that you haven't seen them yet, but you'll see them. You'll start seeing them actually before the end of class, probably. Okay, questions about how division works? Okay, and then the final thing, which we won't see, but I'll just show it to you for kind of completeness, is composition. So this is like P1 of P2 of this. Okay. The result here will always be a polynomial. And the degree of the polynomial will actually be the degree of P1 times the degree of P2. Okay? So when you do this, first, let me add some dashes here. I forgot those. Okay, when you think about what this looks like mathematically, it helps, usually you do it inside out. So you start with the inside. So that's P2, you have P2 on the inside. So I already have what's here. What is here is exactly what is here. Okay? So this is the same as this, which is the same as this, right? Everyone agrees? Okay. What does this notation say? It says, well, P1 of this, okay? So what I'm doing is I'm taking a copy of this and I'm putting it in the box of P1. And then I take a copy of it and I put it in the box here. And then I take a copy of it and I put it in the box here. Okay? So I'm going to have C0 times this whole polynomial to the power of 0. And then I'm going to have C1 times this whole polynomial, but I'm putting the whole polynomial to the power of 1. That's not going to do anything anyways. And then I have C2, and I'm putting this whole polynomial, but I'm squaring this whole polynomial. So I'm taking this polynomial, I'm multiplying it by itself, and then I multiply it by C2. And when I multiply it by itself, I'm doing the long multiplication, okay? And so, anyways, I don't want to draw it out because it's really long. It's going to be really long to draw it out. But that's what this composition means, okay? We're not going to see composition in this course, so you don't have to worry about it. I won't test you on it. I won't ask you any questions about it. But just for completeness, you can see it. And so that's when the degree multiplies, okay? So with addition, if they're both degree d, then it results in a polynomial of degree d. With multiplication, if it's degree d1 and d2, you get degree 1 plus degree 2. Here you get degree 1 minus degree 2, and then here you get degree 1 times degree 2. Okay, questions about doing arithmetic on polynomials? Yeah.
I'm just thinking
Yeah.
You mean like the numbers are the same? Or?
Yeah, exactly. So like R1 here would be like a 5 and a 7. Yeah. And visually, let's just think about what that means. So remember, a root is when it crosses 0. Yeah. So what it would mean is that at R1, the line would cross 0. At, say, R2 is here, and at R3. So the polynomial would look something like this. Yeah? And then for P2, it would have to cross at exactly the same points. Yeah, so if whoops. So let's say it went like this, and then it went like this. Sorry, a bad polynomial. But because it crosses at the same 3 values, it has the same roots. They're not the same polynomial, but they do have the same roots.
Okay, so how does that apply for the division?
So if they have the same roots, then the result, when you divide them, things will cancel out, and you'll be left with a polynomial at the end.
Just the number.
So in this case, it's just a number because the roots, because P1 has 3 roots and P2 has 3 roots. But more commonly, what we're going to do is we're going to take, actually we do this a lot. But you could also imagine that like P1 has 100 roots and P2 is just like 3 roots. And so when you divide it, you're just showing that it has those 3 roots in common. So the number of roots of P2 has to be less than P1. Yeah, otherwise you get a negative degree polynomial, which doesn't make sense. Okay, yeah. So that would be in how you would,
How do you do the inverse of polynomial?
yeah, so the inverse would come in terms of how you actually want to compute this, right? And so the inverse of P2 would be another polynomial. And when you multiply the 2 polynomials together, they equal 1, which is a polynomial, right? It's a polynomial with coefficient 1 and coefficient zeros for everything else, yeah? And this also is why this division isn't always going to work, is you might not have an inverse polynomial that will give you a 1 in the first coefficient and 0 everywhere else, yeah? But when we do it, we will, anyways, the P2s that we use here are always going to be very highly structured. We're not going to just have like completely arbitrary polynomials. We're always going to use a very, very well-structured P2. And so we just have to figure out how to do the division for that kind of P2. We're not going to think about it in general. Yeah. Okay, other questions? All right. Yeah, so don't worry about let's worry about how to do the division when we get to the division itself. Until we get to it, we won't worry about it. Okay, the last thing I want to spend a little time on, but I don't want to like go into a lot of detail on it, is I want to show you interpolation. I have a write-up of it on a website, and I'll put the link in to Moodle. Okay, but I have a concrete example of what interpolation looks like, and so we'll work from this example. So here's an example polynomial. And so far we've been using q equals, I forget, 11 or something small. So this one's a little bigger, but it's still like a small enough number that you can kind of see it. So q here is 97, okay? So what that means is all of this is mod 97. And I won't write the mod, but so every operation we do at the very end will mod 97, and so you're never going to see a polynomial you're never going to see a coefficient that's bigger than 97. Okay. All right. What's the degree of this polynomial? Okay, so it's 7. Okay. How many coefficients does it have? 8. It's always degree plus 1. Okay, just because the exponents count from 0, because there's a 0 exponent here. Okay, so we have 8 coefficients. Now, what's interpolation? So remember, interpolation is where I start with a set of points. Okay, so I have an x value, and then I have p, right here, p at that value. Okay, and then I have another point, and I know the polynomial at that point, and then I have another point, and I know what the valuation of the polynomial is at that point. And then interpolation is I draw a line through those points, and then now I have the polynomial, and I have it in coefficient form. Okay, so that's the output. What does it mean to draw a line through? Well, drawing a line through just means converting it into coefficient form. Okay, so you can think of interpolation as moving between 8 coefficients and some number of points on the polynomial. How many points do we need on the polynomial in order to figure out what the polynomial is? If the polynomial is, let me make it a little more concrete. For this polynomial, the degree of the polynomial is 7. The number of coefficients is 8. How many points do I need to know in order to be able to fully specify this polynomial? Okay, so d plus 1. So d is 7. D plus 1 is 8. So I need 8 points. If you want to convince yourself of this, don't think about degree 7 polynomials. Think of like a straight line. Okay? A straight line is degree what? Degree 1. How many points do you need to specify a straight line? So I know exactly what the straight line is. If I only have 1 point, there's lots of lines that intersect that point. Once I have 2 points, I can draw a line through it. If I have 3 or 4, then that's fine. Then it's overspecified, but that's fine. Okay? So whatever the degree is, I need degree plus 1. Then I can draw a line through it, and it will be exactly the same as the coefficient. Okay? So I can convert 8 coefficients into 8 points, and I can convert 8 points into 8 coefficients. Okay? So we call this evaluation. And we call the other direction interpolation. Okay, so you can go in both directions. If I have a bunch of coefficients and I just want to find, like say you're like, I want to know 8 points. Don't tell me the coefficients. I don't want to know the coefficients. I don't know why. But for whatever reason, I want to know 8 points on this polynomial. I can then reconstruct it if I need to, right? I can compute 8 points on this polynomial, and I could send it to the person instead, okay? How would I compute 8 points on this polynomial? So let's say I'm starting with a polynomial, it's in coefficient form. Now what I want to do is I want to compute 8 points that are on that polynomial, unique points, so at different values. How do I do it mathematically? Okay, so I just pick, first off, I have to pick what points do I want to send. What do I mean by that? I mean, what are the x values that I want to send the points at? Okay, so let's start in the evaluation direction first. So evaluation. So in this case, I have coefficients. And what I want to do is I want to convert it into a set of points. Okay. Okay, so here are the coefficients. I just reversed the order. So 44 is the lowest coefficient and 81 is the highest. But in this format, I'm just reversing it. So this is the one that corresponds to box to the power of 0, and this is the one that corresponds to the box to the power of 7. Okay, so I could just send the set of coefficients, say they're 44, 45, 83, 60, 59, 11, 57, 81. Then you can write out this equation, okay, and now you know what polynomial I'm talking about. Or I could send you a set of points. So here's a set of points. This number, so at point 1, at x value 1, the polynomial is 52. At 2, it has value 59. At 3, it has 69, et cetera, okay? So these are like the x values. Okay, we call it the domain. Okay, so the domain is this set of values here. And then this is the evaluations at those values. Okay, and the whole thing we can call points or evaluation points. All right, the word evaluation. Okay. Now, with these set of points, I have 8 of them, so can I turn it back into coefficients if I want to? I can. Okay, I have enough points. I don't know what the algorithm is yet for doing that, but if I have 8 points on a polynomial that's degree 7, I can turn it back into the 8 coefficients that I need. That's interpolation. Okay. This domain here, I chose to give you points at 1, 2, 3, 4, 5, 6, 7, 8. Are those the points that you need in order to have enough points on the polynomial in order to turn it back into a polynomial? Or is it just sort of arbitrary, like I just chose the first 8 points? So think about a straight line. I want to tell you what a straight line is, but the only thing I can tell you is 2 points on the line. So I can tell you what's its value at point 1, and I can tell you its value at 2. Once you have those 2 values, you can draw a line through it. Okay. Now, what if I told you the value at point 8 and I told you the value at 11? Could you still draw the same line? You still can. Okay. So it doesn't matter where I'm telling you the points. I have to give you 8 points that are on the curve, on the polynomial. It doesn't matter which 8 points I have. Okay. So the domain is, you can choose it. Okay. So it doesn't have to be this. The coefficients you have no choice over. The coefficients are the coefficients. They define the polynomial. Once you choose a domain, the evaluations are locked, right? They are what they are, right? That's the polynomials defining them. But the one degree of choice I have is I could choose the domain if I wanted to. Okay? So we'll come back to why that's important in a second. Okay, so I have this. And now I want to actually compute this. Okay, so how do I do it? So let's start with the number 52 here. How do I get that number 52? Where does that come from? Why is that number 52? Okay, so what I do is I take my equation. I'm evaluating it at 1, okay? So what that means is I'm taking 1 and I'm putting it into every box. Okay, so these are all 1s now. And then I just add up everything, and the answer I get here is 52. Okay? So that tells me that this polynomial evaluated at the number 1 is 52. Okay? If I want to know what the polynomial is at value 2, I do the same thing, except for I put a 2 in every box, and then I add it all up, and the answer will be 59. Okay? And then I can keep going, and if I do P of 8, and I put an 8 into every box, then I get 36. Okay? And this, you can check the math in it. It's actually correct. It's not just made up numbers. Okay, so that's how I went from a set of coefficients to a set of evaluations. Does that make sense? Okay, now a way that I never like to do, because I'm not like big on matrices, but a way of thinking about this that makes it really clean, or a notation for this, is actually to think about it like a matrix. Okay, so we can put this whole thing in matrix form. First off, just in terms of this, I have it all written out here. I'll just paste this in. Okay, so that is what we just did. It's just, you can see it's written out. So I put a 1 in, and then I put a 2 in, and then I put a 3 in, and then you can see the answers come out, and the answers are these numbers here. Make sense? Okay, so alternatively, I could put this in matrix form. So it's the exact same math, it's just in matrix form. Okay, so these are my coefficients, 44, 45, 83, or going back to the equation, just going from the right, 44, 45, 83, 60, okay? So 44, 45, 83, 60, so these are my coefficients. Okay, these are the points, so I'm evaluated on 1, 2, 3, 4, 5, 6, 7, 8, and then what I have here is every power of those. Okay, so the box to the 0, the box to the 1, the box to the 2. Okay, so that's here. You have the box to the 2, the box to the 3, the box to the 4, the box to the 5. Okay, and if you remember with matrices multiplication, you take the first row and kind of put it here like this, and then you go column by column and multiply, and then you're going to get the exact same answer as here. Okay. Okay, so this is just the same expression. All I did is what's 1 to the power of 0? It's 1. What's 2 to the power of 1? It's 2. What's 6 to the power of 2? Well, it is mod 97, but anyway, 6 squared is 36, and that's smaller than 72 anyways, okay? So this matrix is the exact same thing. So now it's all numbers, and this number times this number, I can solve for it, and I get this out as a result, okay? What is this? This is the set of points here, 52, 59, 69, 81, 36, okay? So if I look at this, this is my coefficients. This is the points, the evaluations. And it's not so easy to see. I'll just circle it here. And this is my domain. This is the set of points that I chose to execute it on. Okay, so I decided I'm going to do it on points 1, 2, 3, 4. Those are the points I'm going to give you. Okay. I will say a few more things about this. Let's say I come to you and I say I have a degree 8 or degree 7 polynomial, and I want you to have the ability to convert between points and coefficients, or coefficients and points. Okay? But I have not told you what the polynomial is. The only thing that you know about the polynomial is just that it's degree 7. It has 8 coefficients. And I can tell you the domain that I want to evaluate on. So the points that we'll use are 1, 2, 3, 4, etc. Okay? Can you compute this matrix at this point, even if you don't know what the polynomial is? Okay, so if I go back to this diagram, I have 3 things. I have the set of coefficients, I have the domain, and I have the set of evaluation points. The coefficients, obviously, that's tied to the polynomial itself. The actual evaluations of the polynomial are tied to the polynomial itself. The domain has nothing to do with the polynomial. I can choose that ahead of time. Okay, these 2 things are already in this equation. Okay. This thing, this big ugly matrix, not so ugly, it's actually pretty structured, but this matrix here is just the domain. It's the domain to the power of 0, the domain to the power of 1, the domain to the power of 2. It has nothing to do with the polynomial itself. Okay? So if today you want to convert a polynomial with these coefficients, then you just fill in this value, and then you compute what this value is. Tomorrow you have a polynomial, it's the exact same size, but it's a different polynomial, it has different coefficients. You're going to replace these values with your new coefficients, and then you'll compute the new evaluation points. But this matrix will always stay the same. Okay? So this matrix it's independent of the polynomial itself. Okay, so it only has to do with the domain. So the domain okay, so if your domain's always the same, you compute this matrix once, you store it on your computer, and then that's it. Then you just grab it, and then you just have to do a matrix multiplication. Okay. Okay, last thing I want to ask, it's probably actually easiest to see in this form. How many multiplications am I doing? Just to tell me in terms of the degree of D. So, or you can think of it as like, there's 8 points, 8 coefficients. How many multiplications am I doing? Say it louder. 7. No, more. Across the whole thing. So to compute all of these equations, 64, right? So I have 8 equations, and every equation has 8 multiplications in it, okay? So in general, and how big is this matrix? It's 8 by 8, or 64, okay? So this matrix is always going to be D plus 1 by D plus 1. That will be the size of it, okay? These will be D plus 1. And the length of this will be D plus 1. And the complexity of doing this is going to be D plus 1 squared, which normally we just get rid of the plus 1s and things, so we think of that as OD squared. Okay? So the amount of work that I have to do to turn a set of coefficients into a set of points is the degree of the polynomial squared. Okay? So if I have a degree 100 polynomial, I'm doing 100 times 100 work in order to turn it into it, okay? If my polynomial gets really big, let's say it's 1,000,000 coefficients, doing D squared is actually kind of expensive, okay? It starts to my MacBook Air starts to sweat a bit if I want to get it to do that, okay? So I really don't want to do D squared. What I'd like to do is something less. D would be great, But what I would settle for is d log d, and we showed last time that d log d is very close to d, and it turns out that we can do that. Okay, so there is a way to get it down logarithmically, but we'll eventually get there. Okay, so right now I'm satisfied that I can turn coefficients into a set of evaluation points. It's pretty straightforward. I just plug in the values, I evaluate the polynomials, I get the answers. Or if I want to think about a matrix, I can think of it in terms of matrix multiplication. They're equivalent to each other. Okay. Now I want to do the opposite. I have a set of points, and I want to turn them into the coefficients. Okay, so we call this interpolation. Sometimes it's more the application of why you want to do this in real life, but sometimes we call it fitting. So you have some data, which is a set of points, and you want to fit a polynomial to it. So you're going to interpolate a polynomial through those points. So you can think of it as sort of fitting a polynomial to it. Okay? How are we going to, any ideas about how on earth we're going to do interpolation?
Matrix inversion.
Great, that's exactly it. Okay, so I have this matrix, and here I have my set of coefficients, and I'm computing my evaluation points. If I want to go backwards, if I want to start with my evaluation points and convert the coefficients, all I have to do is take this matrix and move it to the other side. Okay, so if I move this matrix to the other side, then I can do interpolation. So that's all interpolation is. It's basically, once you put it in matrix form, it's just, I got to move it to the other side. What does it mean to move the matrix to the other side? Okay, I have to invert the matrix. Okay, so I'll just show you in terms of here. I won't put it in the notes. So I have this. And what I want to do is I want to move this to the other side. So what I do is I invert it. So I take the matrix, I move it over, I invert it, and now I have this equation. Once I apply the inversion to the matrix, then all the coefficients change. How you do inversion, like how you invert a matrix, the algorithm for it, you don't have to worry about. Again, this matrix has nothing to do with the polynomial itself. Okay, this is something that it just has to do with the domain. So because we chose points 1, 2, 3, 4, 5, 6, 7, 8, this is the matrix for 8 points on the domain 1, 2, 3, 4, 5, 6, 7, 8. It will always be the same. Everyone will have the same matrix itself. Okay? So the figuring out what these matrices are is something that you sort of just do once. And then once you figure it out once, then you are good. So I'll just grab a copy of this. Okay, so now we have our points, our evaluation points. We have the domain. And I can solve, so like normally this would be, I wouldn't know what these values are, but I'm going to do the math here, and then I'm going to solve for the set of coefficients. Okay. Algorithm's exactly the same. The only difference is the matrix itself changes. So the complexity of this algorithm is also going to be d squared. And it's the same algorithm. It's just a matrix multiplication. It changes. Can I always compute the inverse of a matrix? Are there certain matrices where I can't, where there is no inverse, or an inverse isn't well defined? So the answer is yes. Like say there's a repetition of rows. Like say I had this row 3 times. Then I don't have enough independent rows in order to convert the, and that makes sense. If I have a bunch of, like I say I give you 8 points and you can draw a curve through the line, But what if I just give you the same point 8 times? You're not going to be able to draw the curve through the line, right? Or if you're trying to get a straight line and I tell you its value at 1 is 2, oh, and its value at 1 is 2, you don't know what the line is, okay? So you need 8 independent points, and the way you'll get caught is you'll try and do this inverse and it's not going to work. The algorithm's going to not work because some of these rows are independent, okay? So I'll make a note of that. So this is possible if rows are independent. And so it's sort of, in the polynomial interpretation, what it means is that you have 8 unique points in the domain. Okay, is there any way that we could probably do this matrix multiplication any faster than d squared? So just visually looking at it, is there going to be, do you think, some way that we could do it faster than d squared?
There's a way to do this minus square something like fit, does it help?
Maybe, maybe not. That's not what I'm thinking of yet. Okay, so it's hard to see how there could possibly be a way because at the end of the day, this number has to touch every number here. This number has to touch every number here. This has to touch every number here, right? And so I'm not really seeing it. But intuitively, what I could think is maybe I could kind of break this up into chunks. And then I would do the multiplication in chunks and then sort of combine the chunks together, right? So what it would look like kind of would be, so instead of doing this big matrix multiplication, what I would do is I would take a smaller matrix and I would take the first half of the values here and it would give me the first half of the values, and then there would be some other matrix, and if I had these values here and these values here, then I would be able to then I would be able to do it in less time, okay? And then if I could play this trick, if I could decompose it like this, then I could do this again. So I don't want to do this multiplication, it's too big. So I could take half of this matrix and I could keep going until it gets really small, then I would evaluate them all. So it's a typical kind of logarithmic kind of thing where you break it in half and then you break it in half again, then you break the problem in half again. Eventually it's small enough, then you do the problem and then you take the results and you filter them all out, okay? The problem with this is that we don't think this works. We don't have a good way of doing this split for an arbitrary matrix. Okay, so we don't know of a general mathematical technique where if I just give you a matrix here, you can just split it up like this, okay? But there's one trick that we still have left at our disposal, and I've mentioned it before, but the domain, the fact that I tell you the points at 1, 2, 3, 4, 5, 6, 7, 8, do I have to give it to you at those points, or can I give it to you at any 8 points? Any 8 points, okay? If I change these points, let's say I change them to something completely different, what changes in this equation? So now I have a different set of points. Okay? The only thing that changes is this matrix here. Okay? These two things are just my polynomial represented in 2 forms. So this matrix would look different. Okay? So I can try a whole bunch of different domains and then I can generate a whole bunch of different matrices. Okay? Then I can invert them, and same thing here. This matrix will change as well. And I can try lots and lots of domains, and I can look at what's the matrix that comes out. Okay, is it possible that maybe there's a matrix that's nicer, right? So I'm looking at this matrix, and I'm like, I have to do a multiplication with this matrix. There's no structure or anything to this matrix. You know, it doesn't look like a nice matrix, but maybe there's some kind of matrix that's nicer. Okay. So there are matrices that are nicer. So one example of a matrix that might be nicer is if I change my evaluation points from 1, 2, 3, 4, 5, 6, 7, 8, what if I just copy what's here? Okay, so if I make my evaluation points what's in the row here and put it in the column, that's what I do here. So you can see I have 1, 2, 4, 8, 16, 32, 64, 31, and then I have the same points here. What can you tell me about this matrix here? This matrix is symmetric along the diagonal, right? Every number here has a matching number here, okay? So this matrix has better structure than the matrix I was using. And in order to use this, all I did is I changed the points that I'm evaluating at. So instead of evaluating at 1, 2, 3, 4, 5, 6, 7, I'm evaluating at 1, 2, 4, 8, 16, okay? Then if I want to go in the opposite direction for interpolation, I have to invert this matrix. So this is the inversion of that matrix. So this inverted is the same as this. Is there any structure in the inverted matrix? Okay, it also is symmetric as well. Okay. All right. So this is nicer than the other one. Yeah. Okay.
Is the powers of 2 important, or we could do it in 3?
Sorry, I just got lost thinking about something. What? Say again.
Is the powers of 2 important, or we could do it in 3?
Yeah. So that's the question I want to ask. So like, what are a set of domains here where we can generate something that's symmetric? Yeah. So we'll talk about what powers you need and things like that in a second. Yeah. Okay. Okay, for some reason I have a mistake in this write-up. I'll have to go back and recheck it. I was thinking for some reason that when you do the inverse, it ends up not being symmetric, but it clearly is symmetric. I think it's because of I can pick other points. Anyways, I'll fix this later. But this is exactly what we want, actually, in both cases, is we want something where the initial matrix going in one direction is symmetric, and then the inverse matrix is also symmetric. Okay, and there's going to be different domains that give us this property. Okay, but I don't know the mathematical rule yet for how to figure out the domains that give me this value. Now, I don't want to go through this whole algorithm. It's going to take too much time. But if you can get these two symmetric, then there is a way where you can kind of split your evaluations in half. And so you can kind of work on the top half and the bottom half of the matrix. And then there's a way to combine them. And then you can do that trick again where you can take the smaller combination and split it in two and split it in two. And so the whole thing ends up being n log n instead of n. Okay? So you split in half n times. So that's where the log n comes from. And then the whole thing ends up being n as well. Okay? So and maybe for the assignment, I might make you go through this yourself, but that was my thought instead of taking a lot of class time to explain it. Okay.
So, what is that for you to find the domain that you want?
We haven't answered that question yet. Yeah. Okay. So is there a nicer domain? And the answer is yes. This is an example of one. And the reason that we think it's nice is because it's sort of symmetric along the diagonal here. Both the inverse and the original. Okay, because of this property, we're able to use something called a fast Fourier transform. So technically, the fast Fourier transform is when you're going when you're interpolating, when you have a set of points and you're going to the domain. And then the other matrix we call the inverse fast Fourier transform. Okay, and it's going to have a runtime complexity of n log n instead of x squared. Okay, so this is better than n squared. And last class, you might remember the little diagram that we drew where we said you might have something that's runs in constant time. You might have something that runs in time n. You might have something that runs in n squared. If you go kind of halfway between the two, you have complexity root n root n. And if you go just tiny, like a little bit over from n, that's where you're going to find n log n.
Sorry, can you restate the outline of this algorithm?
So the fast Fourier transform is just, I use this matrix and I plug it into this. Yeah, so the fast Fourier transform is just, basically it's just a matrix, you find it, and once you find the matrix, then you just do matrix multiplication. Yeah, okay. So FFT, I'll note that. So you have the FFT matrix. And remember, again, it only depends on the domain. It has nothing to do with the polynomial itself. And then, oh yeah, sorry. There's two components to the algorithm. I understand your question now. And then what I'm going to do is I'm going to take my points and I'm going to convert it into coefficients. Now, what does the algorithm do? Well, what it does is instead of doing this as a big matrix multiplication, what it's going to do is it's going to split this matrix into half. Okay, but half of a square is no longer a square, so we're going to break it into more like a quarter. Okay, so we have a big matrix. You can think of it as kind of like this, and we're just going to take that piece, and we're going to take, say, this piece. And then we're going to do the matrix multiplication with these smaller ones. But then we can play this trick again. We can split it into half. And so we can have a smaller one here and a smaller one here. How you do those splits is complicated. And then how you merge, once you do all the multiplications out and you have all the splitted out values, how you merge them back into the whole is also kind of complicated. Yeah, so I'm not going to cover that in this class. It would take 2 lectures probably to go through. Yeah, I may make, as I mentioned, I might make you do it on the assignment just so that I know that you understand it. And I'll link to this write-up that also explains it. Okay, so questions about this at a high level? Okay, so in this class, what we will do is we will try to choose a domain like this domain here, where it gives us a nice set of values. Okay, how we choose that is the next question. Okay, so I haven't shown that to you, but it's about time for a break. So why don't we take? Or yeah, do you have a quick question? Yeah. Yep, so both matrices are symmetric. Basically, all I did is I tried a whole bunch of different domains here until I found one that were symmetric on both sides. And then I said, okay, I like this domain. I'm going to do it. But maybe I just did it through exhaustive search, right? But now I want to write down the mathematical rule for how to compute the domain. Yeah. Okay, I'll see you in 10 minutes. Okay, how to find the domain is something that will it's something that we'll come back to a few times. but we'll see it twice, and I'll explain it slightly differently why. For now, I'm just going to tell you what the domain is. I'm not going to try and motivate why this lets you do fast Fourier transform. You don't really need to know it. And then later, there's another property. There's maybe 3 or 4 properties that using this kind of domain gives you that's advantageous. And so we'll talk about those advantages as we need them. Okay. So here's what you do: is you're working mod Q. Okay. And in our running example, Q is 97. You figure out how many points, your domain has a certain size. You have a certain number of points, which is the number of the coefficients, which is the degree plus 1 of it, okay? So we're working with a domain d plus 1. Okay, so this is the number of coefficients and also the number of points that we're evaluating. Okay, what I'm going to do is I'm going to find a generator of order d plus 1 for mod Q. Okay, or you can think of it as ZQ, it's the group itself. All right, so Q was 97, here d plus 1 was 8. So what I want to do is I want to find some number that generates a bunch of numbers, and it has order 8, okay? How do I do that? Well, I'm going to need, well, there's algorithms for doing it, but the way that we've been doing it in class is just we have these tables, okay? But now it's a bigger, much bigger table. It's table number 90, or it's size 97, okay? And so somewhere in this table, I'm going to try and see if there's something that has, that's a generator of size 8, okay? So first off, let's see, for example, if there actually is one. Yep. Okay. So what I'm going to do is I'm going to find a generator. I'm going to give it a name. Normally, what number, the letter that we normally use for a generator is G. Because this is a generator that has other purposes, we're going to call it omega. It's just like what's standard in the literature for this specific kind of generator. So I'm going to find a generator W of order d plus 1 for ZQ. Okay, so ZQ is Q is 97. I have an exponentiation table for 97. So if you want to know what 5 to the power of 3 is mod 97, then this value, it's going to tell you that the value is 28. Okay, we've seen this table before. It's just we're using a smaller table. Now we're using 97. Okay.
So the order of the generator doesn't matter. It's just it should include those numbers. Right?
No. I want a generator that has order d plus 1. Yeah. So what I want is an omega equal to something. Okay. So I don't know what that something is yet, and the order of omega is 8. Okay. All right. So maybe I think 3 is that number. Okay. What's the order of 3? How do I figure it out? Actually, let me do 4. It's a little nicer. What's the order of 4? Okay. So it's 20 or 24. Okay. So how I do it, I go along, and eventually I'll hit a 1. And when I hit a 1, it's going to start repeating. Okay. So I found something of order 24, okay? But I want something of order 8, okay? So that's not it, okay? So I can keep going. Here I see 6. What's the order of 6? 12. Yeah. It goes to here.
You have to look for 1, 8.
Okay, so that's a good trick. So what I want to do is I want to see a 1 that's going to show up in the 8th column. Okay? If I see that, then I'll know it's order 8. Does that make sense? Okay, so I'm going to scroll down. Tell me if you see something. Okay, so the number 22 here is, yeah, so it goes to 1, and 33 is as well. Okay, so these are all possible numbers. Oh yeah, sorry, you're right, yeah. So this is another thing that you should always check. So at 22, it does repeat at 8. So that's a necessary but not sufficient condition. So you have to see a 1 here, but you cannot see a 1 earlier as well. So you actually have to check that you don't see it earlier. Yeah. Sorry, say it again. Yeah, it would repeat twice, and so this is order 4 instead of order 8. And then if I say, let's do point, the x value will be 1, 2, 96, 75, 1, 2, 96. I'll repeat the points and it won't work. Yeah. Okay. All right, so 33 looks like the smallest one that is properly. Okay. So I don't know yet. I just know, I know that 33 works. Okay. So 33 works. So I'm going to write in 33. Okay. And then what I'm going to do is I'm going to generate the group. So it's going to be w to the 0, w to the 1, w to the 2, w to the 3, all the way up to w to the d. Okay. And so what that group will look like is going to be 1, 33, 22, 47. Let's see if I can just copy and paste that. Okay, I'll just copy it and then I'll delete that because it's kind of in the way. 1, 33, 22, 47, 96, 64, 75, 50. Okay, and what I'm telling you is if I make this my domain, okay, then FFT will work. I'm not telling you why that's the case, but if I set this equal to my domain, I'm able to do FFT as opposed to doing the n squared matrix. I can always do matrix multiplication. Okay, that's called Lagrangian interpolation. So I can always multiply it out, but it's going to be order d squared. If I want a shortcut and I want to do it in n log n instead, so instead of being here, I want to go all the way to here, then this is how I find that domain. So that's another question. So 33 is part of this domain. Does that mean, or sorry, let's say 96. So 96 is part of this domain. Does that mean 96 itself has order, has the same order, has order 8? And the answer is yes. All of these elements will have at least order 8, but they may have order that's smaller. So they'll either be order 8 or they'll be a smaller order itself. So we actually looked at 22 already. So 22 was the example where there was a 1 here and we got really excited, but then we noticed, oh, there's a 1 here. Yeah. So if we look at any one of these ones, so let's take 96, there's going to be a 1 in that column. So in the 8th column, there is going to be a 1 there. That's the guarantee, but there might be ones somewhere earlier as well.
The reason that we can't use these numbers is we can't do the copy like this, or we can't do it.
You mean like how do I find?
So I will ask
Okay. All right. So there happened to be this number 33 that had order 8. So I was working on 97. I wanted something of order 8, and there happened to be a generator that generates something of order 8. Okay, in this table. Is there going to be a generator for every number? Okay, so let's say I want something of number, let's say I want it to generate order 3, okay? One has a 1 there, but it also has ones earlier, so it's not order 3, okay? Is there a 1 anywhere in this column? Okay, so there is, okay? So that's good, all right? Now let's say I want order, I don't know, 17, okay? Again, there's a 1 here, but this isn't order 17, it's order something smaller. So then I go down this column. And oops, there isn't a 1 anywhere in that column. Okay? Or sorry, there's not a 1 where it's the first one in that column. Okay? So there is nothing of order 17. Okay? So what that means is I can't just go around choosing once I set my d+1 value, I'm not necessarily going to find something of the right order. Okay? So what orders exist? Now I need a mathematical rule that tells me what are all the orders where there's a generator of that order. Okay? We know the answer, you just might not connect it because we talked about it when we talked about GQ. Okay, it's the same answer as before. The answer is that, so we'll have generators of order alpha for any alpha that divides q minus 1. Okay, what's q? 97. Okay, so what are the divisors of 97? It's minus 1 equals 96. Okay. And so there's going to be a bunch of them, right? And so and 8 is one of them. Okay. So there's going to be a bunch of divisors of 96, and you're going to have orders of that size, and you're not going to have orders of other things itself. Okay. In practice, what's going to happen is NIST or some government is going to tell you, here's a queue that you can use. Okay. And what they're going to do is they're going to make sure that there's a whole bunch of divisors of q minus 1. Okay? And the way that they're going to do it is they're going to say that 2 to the power of some big number is going to divide q. And let's say that this is like 32 or something. Then if 2 to the 32 divides it, then 2 to the 31 also divides it, and 2 to the 30 divides it, and 2 to the 29. Basically, every power of 2 less than 32 will divide it. Okay? And what that means is that the size of your domain, you can choose the nearest power of 2. So you have a domain of size 2, 4, 8, 16. And the consequences of this and why it matters, you're not going to know for a couple weeks still. So we'll just put a pin in it for now. But I'm just planting this seed of the idea that we choose a generator of order omega. Okay? Now, the final thing I would note is just a sort of notational note. Okay, so I said the order of omega equals d+1. And I'm just going to make this 8 for a second here. Okay, what's another way of saying the order of a w equals 8? Well, another way of saying it is w to the power of 8 equals what? Equals 1, right? Because we had a 1 in the 8th column. Okay, so an implication of this is that w to the 8, or omega to the 8 equals 1. Okay, if we solve for omega, we get the 8th root of 1, okay? And the number 1, sometimes people call it unity. It's just sort of a term that's used for elements that behave the way that 1 is behaving right now. Okay. Again, you don't have to follow this at all. I'm just establishing notation. Okay. And so what people will do is they'll either say the order of omega equals 8. That's the clearest way of thinking about it from my view. But if you pick up a paper or you go to a research talk and people are talking about it, they're going to say omega is an 8th root of unity. Okay, so you'll see that terminology everywhere when you start reading things. And the first time I saw it, I had no clue what that was. I was like, what's a root of unity? It reminds me of like these like crazy diagrams that we used to see in electrical engineering. And so anyways, it took me a long time, but then once I realized that, oh, it just means that the order of omega is 8, then it was a lot easier to understand. Okay, so anyway, so we'll talk about roots of unity, or the domain is the roots of unity, and that's just some terminology, but what it means is exactly this. Okay, so in general, it would be the d plus 1th root of unity is what you want. Okay, we'll come back to roots of unity later when we need it. We don't need it now. Well, we needed it just because we get fast Fourier transform. At this point in the lecture, you can draw a big black box around interpolation, and just know there is an algorithm. It does it in n log n time. And so if I have a bunch of points, I can turn it into coefficients. If I have a bunch of coefficients, I can turn it into points. It's going to take n log n time. I'm in this kind of weird domain. But other than that, the algorithm works. It's like a button on my calculator. I just press it and it does it. And how it does it doesn't really matter. Okay, and you don't really need to know how it does it either. Okay, that was a big topic. There's one other thing I want to talk about, and then we're going to go to the main event, which is committing to polynomials. Okay, so imagine a scenario. It's kind of a weird scenario, but let's think about Alice, and Alice is thinking about her favorite polynomial. Or let's say that there's some other party like Bob. Well, we'll do it Alice and Bob. Let's say there's Charlie goes to Alice and says, here's a polynomial, I want you to remember this polynomial. Okay? So Alice is thinking about her polynomial. And here's Bob. And Charlie went to Bob and also said, here's a polynomial, I want you to think about this polynomial. I want you to remember it, write it down. Okay? So Alice and Bob both have polynomials, they're both thinking about it. And Alice and Bob start talking and they're like, Alice is like, Charlie gave me this polynomial. And Bob's like, oh, that's really weird, Charlie gave me a polynomial as well. Do we have the same polynomial or not? Okay, so they want to just ask each other, do we have the same polynomial or not? That's a simple question. Okay? How are they going to do that? Okay, so they can send any message they want back and forth about their polynomials. And they just want to know at the end of the day, do we have the same polynomial or do we have a different polynomial? So what's one thing that they might do? A simple thing. This isn't a trick question at all.
Sharing the polynomial.
Okay, and what does that mean though?
Sharing the coefficients.
Okay, so what Alice could do is say, here's the coefficients of my polynomial. And Bob would be like, okay, yeah, those are exactly the same as my coefficients, or they're different than my coefficients. Okay, how many values do I have to send back and forth? So the degree, which would be d plus 1. Okay, so I can send d plus 1 coefficients. Okay, using what we were just talking about, interpolation, is there something else I could send instead of d plus 1 coefficients? I could send d plus 1 points. Okay, so I could say, here's a bunch of points, and then what Bob will do is he'll check those points on his polynomial and he'll decide if they're the same or not. Or he can interpolate it into coefficients and check against it. Either way he wants to do it. Okay. And, yeah.
Is it assuming both polynomials are the same size?
Sorry, say it louder though.
Is it assuming both are the same size, or?
Yeah, so we can say that maybe the first thing they check is the degree of the polynomial, and so they just exchange the degree, but yeah. So we'll assume that that they both know it's degree D. Thank you, that's a good point. All right, so they both agree it's degree D, then they check D plus 1 of the coefficients or D plus 1 of the points, independent points, and then now they're happy, they know whether it's the same polynomial or not, okay? What if they started checking the coefficients and the first one was the same, the second one was the same, the third thing was the same, the fourth was the same? Do they even have to bother to check the fifth one? Or could they just say, well, the first D of them are the same, and so maybe it's the same polynomial? Okay, so it's not sufficient at all, okay? If these two things differ by just one coefficient, it could be a completely different polynomial. If it differs by just 1 point, it could also be a completely different polynomial, okay? So my confidence, and if Charlie knows that they're lazy, and maybe he wants them to think they're the same polynomial, he might pick two polynomials where the first D points are exactly the same, and they only start differing at the D plus 1th point. Or same with the coefficients, okay? You might pick two polynomials that look almost the same itself, okay? So, are they the same or not? Let's say that we do a comparison, and this is like how many points that we compare. So, I'll write it in coefficients, but it's the same as points. And on the y-axis, this is how confident I am between 0% and 100% of whether these two polynomials are the same. If I compare the first coefficient, I'm not confident. I have 0% confidence. If I compare the second one, I'm still at 0. I'm at 0, I'm at 0, I'm at 0, all the way up to D. And then when I check that D plus 1th point, then my confidence goes from 0% to 100%, okay? So if I'm going along here, it goes from 0 to 100. Okay, so I have no confidence, and then I check one more point, and then now I'm 100% confident. It couldn't possibly be a different polynomial, okay? That's the point I'm trying to make. So once you check D plus 1, do you have to check D plus 2, D plus 3? If you know it's degree D, then once you check D plus 1, then the polynomial is now locked. And so checking additional points doesn't help you at all, or additional coefficients. Well, there are no additional coefficients, but additional points. Okay, so this is fine? Okay, now here's a question. What about, okay, I buy the argument that if you check D out of D plus 1 coefficients, the last coefficient could be anything at all, okay? If I check D plus 1 points, sorry, if I just check D points instead of D plus 1, I'm lazy. I don't want to check D plus 1 points, I want to check something less. So I'm just going to check D points, or half of D plus 1, or something like that, okay? Is it really the case that I have no idea whether it's the same polynomial or not, right? So we start checking, and let's say the degree is 100, and I check 50 points. Is it really the case that like my certainty that the polynomial, and they agree on all 50 points. So at the end of the day, I know that they agree on all 50 points, okay? But I know the degree of the polynomial is 100, so I need to check more points. But am I really at 0%, or am I at least like a little confident? I'm trying to build some confidence, right, that the polynomials are the same, right? It seems like I'd be a little more certain than 0%. Okay, so that's a great observation. It depends on who chooses the points, right? If the points that I'm checking at are the points that Charlie chose, and he gave me the two polynomials, then he could program them to have the same 50 points. First 50 points agree, and then they start disagreeing after that. Okay? What if I choose the points at random? So I choose 50 points at random. Okay? Then could I be at least a little more confident? If they agree on 50 points, it's a degree 100 polynomial, so I'm not 100% sure, but am I more than 0% sure that they're probably the same polynomial? So it definitely seems intuitive, right? It seems intuitive that my certainty, the more points that I check, should kind of go up, maybe something like this or something like that, if I'm choosing points at random. So it doesn't work for coefficients, but it works for points, okay? Why doesn't it work for coefficients? Well, there are only, like, let's look at this concretely. These are the coefficients, and there's only these coefficients. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8 coefficients. They're exactly those 8 coefficients. But how many points are there on this polynomial? Okay, there's 97 of them, because we're working on 97. So I can plug in any number here. And so there's only 8 coefficients, but there's 97 points. Okay, so there's a lot more points. And so it's somehow, maybe that seems like that it's going to help me somehow, but we're not sure. Okay. All right, so let's work out what's the probability of if I just send 1 point. And then once we know what the probability is for 1 point, then we can figure out what it is for 2 points and 3 points just by multiplying. Okay. But the important caveat here is it's going to be a random point. Okay, so what's the probability that Alice's polynomial, I'll put it as PA, that's Alice's polynomial, and Bob's polynomial have the same value at some random point that I pick. I'm going to use a really fancy Greek letter. I'm going to write it kind of like a squiggly, which is zeta. Actually, you know what? I reversed my thinking on this. I'm going to use the number tau instead. I like tau. Okay. So what's the probability that the polynomial at tau of Alice's is the same as for Bob, where tau is randomly chosen? Okay, what do we need to know about polynomials in order to compute this probability? So a probability is going to look like the number of chances that it's the same sort of divided by the total number of chances. Okay, so we're going to have a numerator and we're going to have a denominator. Okay, let's talk about the numerator itself. Okay, what's the chances that two polynomials have points in common, period, whether it's at tau or not at tau? Okay, let me sharpen the question a bit. I give you two polynomials. How many points do they have in common? Let's think about a straight line. I give you two straight lines. How many points do the straight lines have in common? One, unless if they're the same line. If they're the same line, they're going to have all the points in common. And if they're different, they're going to have exactly one. They're going to intersect at 1 point, right? Can they intersect at like 3 points and then stop intersecting? They can't, okay? And so polynomials, just sort of graphically, let's say you have a polynomial that's like this, P1. You'll never have a polynomial that's like, it's a different polynomial, but then it kind of joins up with the polynomial for a bunch of points. and then it kind of diverges. Okay, so like it's the same thing here. Okay, that basically that doesn't happen. Okay, you can't have a segment of a polynomial that are all the same things. It's going to have an explicit number of points where it intersects. So if you zoomed in on this, what you would see is something that looks more like if you zoomed in on that segment, you would see, instead of it following exactly, it would kind of like bounce around, and there would be a bunch of points of intersection between them. Okay. Okay. Two straight lines. What's the degree of a straight line? 1. Yeah. And how many intersection points do they have? 1. What's a parabola? Think of a parabola. It's degree 2. How many points can a parabola have in common? So you might have a parabola that looks like this, and then you could have one that looks like this, or maybe one that looks like this. They're always going to have at most 2 points in common. Okay, they can't have 3 points in common. Okay, so extrapolating on that, degree 1 has 1 point in common, 1 intersection point. Degree 2 has 2 intersection points. Degree D, how many intersection points is it going to have? D. Okay, so this is a mathematical kind of fact, which is that if the degree of polynomial A is the same, so I'm going to assume that the degree, I should have wrote it before, but I'm going to assume the degree of polynomial A is the same as the degree of polynomial B. Actually, sorry, we did have that assumption here, so we agreed that they're the same degree, and we'll say that the degree is D. So 2 polynomials of degree D can have at most D points in common. It can never have more than D points. Okay? So if I pick 1 point at random, okay, what's the chances that there are actually different polynomials, but they just happen to be the same at that particular random point that I chose? I have D chances. Okay, there's going to be D points along those pairs of polynomials where that could happen. Okay, so my probability is going to be D over the number of random points that I could choose. How many random points could I choose? How many points do I have? Okay, so I have the number of points is, if it's mod 97, the number of points here is going to be 97. So I can put in 0, 1, 2, 3, 4, all the way up. I can put in 96. If I put in 97, well, 97 mod 97 is 0, and so it's just going to reduce to 0. So if I evaluate this at the point 97, I'm going to get the same answer as if I evaluate it at 0. Okay, so the probability here is going to be D over Q. Okay, so the probability that if Alice and Bob are sitting here and they pick 1 point at random, okay, the probability that their polynomials will have that point, will be equal at that point, is going to be D over Q if they're not the same polynomial. Okay, what if they are the same polynomial? Then they're going to be the same at all points. Okay, so we're going to run this experiment. Alice will pick a random value tau, and she'll say, my polynomial at tau is this value. And Bob will say, let's say he says, yes, mine is the same. Okay, one of 2 things happen. Either they have the same polynomial, or they got really, really lucky, and it just, by random chance, it happened to have the same point in common. Okay? All right. So here's the algorithm. So Alice chooses tau at random. It doesn't matter the order, but Alice sends just one value, which is P of tau, to Bob. Okay. And then Bob basically can say, I have a different value, or I have the same value. If he says I have a different value, then you know that they're not the same. Okay, they can't be the same polynomial. If they differ at least 1 point, they're different polynomials. Okay, so PA is not equal to PB, they're done. If it's the same, that means either PA equals PB, or well, it does mean it. Oh yeah, sorry. It means PA equals PB, or PA is not the same as PB with probability D over Q. Okay. All right. How many points do we have to send before D over Q gets so small that we don't care about it anymore? Okay, so if I send half of the points, if Alice sends half of the points to Bob, every time it's probability D over Q. And so if you send 50 points, it's the probability that they're not the same polynomial is going to be D over Q times D over Q times D over Q times D over Q. It's going to get smaller and smaller, and eventually it's going to go to 0. Okay, so you can think of it as sort of a graph here. So here's the probability that PA is not equal to PB. Okay, so the probability that the polynomials are not equal, but the points are. So all the tau values result in the same. It's hard to write out, but basically I'm going to pick a certain number of points, and then so my starting probability. If I send 0 points, I don't know. I have no idea. And then if I send the first point, the probability is going to be D over Q. And then if we do it with a second tau, then the probability is going to be D over Q times D over Q, or D over Q squared. And then it's going to go down to 0, kind of like this. Okay, so at a certain point I'm going to say, and then it will literally go to 0 at D plus 1. As we had here, okay? So at D plus 1, then I'm very certain that there's no way that you can continue to trick me, okay? All right, this maybe doesn't make a lot of sense. I'm not really explaining it that well. Let's just go back to this. If they're different, they're not the same. If they're the same, they're probably the same polynomial, but there is a small chance, a D over Q chance, that PA and PB are different, okay? What kind of numbers would we see for D and Q in real life? Okay, so where does Q come from? Q is a cryptographic number. It's mod, remember we're working mod Q, that's where this comes from. Mod Q, or ZQ. And this is given to us by NIST. And NIST is going to pick a Q that has 256 bits. Okay, so the size of Q is going to be the size of bit is going to be 256 bits. And therefore the number of Q, the number of possible Q values is 2 to the Q. And so notationally, yeah, okay, this is right, I'm just confusing myself. It's going to be 2 to the 256. Okay, so we're going to have, in practice, we're going to have D over 2 to the 256, okay? Polynomials that we're going to use in this class are going to be pretty big, okay? They might be like degree 1,000,000 or a degree 10 billion, okay? That's a big polynomial. If you go much beyond that, then your computer is going to struggle, dealing with polynomials, doing any kind of polynomial math, Okay, so let's just say that the biggest polynomial you'll see is a degree 1 billion. Okay, what is that in terms of 2 to the power of what gives you 1 billion? So I would have to sit and think hard about that, so I'm just going to ask. Actually, I'll just ask. Do you know, sorry?
So around 1 billion is 10 to the power of 9.
Yeah, no, way bigger than that. It would be like 20-ish, I think. Let's just do it. 1 billion. 1, 2, 3. 1 million. 30, yeah, 29-ish. So let's say that we have let's just round up. We'll go to 230. So it would be like a billion degree polynomial. Okay, so what's the probability after just checking 1 point on the polynomial, just one? What's the probability that they end up being this different polynomials even though they agree on that 1 point? So I check that one random point. It tells me that the polynomials are same at that random point. Can I conclude, therefore, that they are the same polynomial? Okay, so this is going to be 2 to the 256 minus 30, so 226. Okay, so the probability is going to be, 1 over this. Okay, so the probability that we're in this case is 1 over 2 to the 226. Okay, is that a small number or not? Okay, that's an extraordinarily small number. Okay, that's like looking at every atom in the universe and picking one at random, and it happening to be the one that I'm thinking of. Okay, so I think of one atom in the universe, you pick one atom at random, and we happen to pick the exact same atom. Okay, and even that number is this is, I think, even smaller than that number. But anyways, so this is just like extraordinarily small. Okay, all right. So what does that mean? What that means is if we want to compare two polynomials, we can actually just pick one random point to compare it at, and that's as good as comparing the two polynomials. Okay, so this probability, basically, what's the probability that two polynomials agree? They agree only at d points. This is called the Schwarz-Zippel lemma. So sometimes you'll see that term. It's just the mathematical name for it. And by Schwarz-Zippel, we just mean that you can pick one point and basically tell whether two polynomials are the same. Okay, so I'll write out the sort of the consequence of this. I'll do it in green. Okay, so given two polynomials, and it doesn't have to be two either, it could be n polynomials, but I'll just write it into two. Testing if they are the same at one random point. Is overwhelmingly the same as testing if they're the same polynomial. So it's not 100%, it's not exactly, but you're 99.9999999% sure. So close to being 100% that you might as well not even bother. So given two polynomials, testing if they're the same at one random point is overwhelmingly the same as testing if they are the same polynomial. Okay. So later, when we get to zero knowledge, what's going to happen is we're going to build some polynomials of things that we want to prove. And in order to do that proof, I'm going to send you some polynomials, and I'm going to tell you that, you know, if I'm not lying to you, then like this multiplied by this polynomial plus this polynomial should equal this other polynomial or something like that. And what you'll do is you'll just pick one random point. I'll open it up. I'll open all my polynomials at that one random point. And if that identity holds at that one random point, it must hold at all the points on the polynomial, overwhelmingly. Okay. So we're going to use this fact itself. Okay, is there questions about this? Okay. Then we're finally ready to commit to polynomials. So now we're going to go back to the idea of commitments. So before we talked about committing to, we had this Peterson commitment where you could commit to a single value. Now what I want to do is I want to commit to a polynomial instead. Okay. Okay, so recall, I'll start with the Feldman. All right, so if I want to commit to message M, and what I do is I just do G to the power of M mod P, where G comes from GQ, Z is in ZQ, and the resulting commitment will be in GQ. Okay. Now, what I want to do is instead of committing to M, I want to commit to a polynomial instead. Okay. So what I can do is I can let's just try to pencil it in and see what it looks like, and then we can try and solve any problems that arise. So I'm going to commit to a polynomial. And so I'm going to have G to that polynomial. What does a polynomial look like? Well, it looks like a coefficient plus C1 plus C2 squared plus C3 Okay. Can I commit to that polynomial as it stands right now? Is it a number? Is that thing in the exponent a number? Because that's what I need. So I need M to be in ZQ. What does that mean? It needs to be an integer between 0 and Q minus 1. Okay. Right now, is this thing a number? It's not. It's okay. What about C0, C1, C2, C3? Are those numbers? Okay, so they are numbers, they're coefficients. So once I pick my polynomial, I'll fill these C values in. What about the squares? They're not numbers, right? They're a polynomial you can put any number there, right? You can evaluate it at 1, you can evaluate it at 2, you can evaluate it at 3. Okay? So that's not a number. Okay? So I can't just straight up commit to it. Okay? So what am I going to do? What I could do is I could commit to it at a point, right? Like I could commit to it at the value 10 or the value 11 or something. Okay, let's go with 10. Then I could fill in the number 10 here. Then I could make this into a number. I will compute it out, right? And remember, exponents are mod Q. And so that's what we've been doing all along. We've been talking about polynomials mod Q. Okay, so I evaluate it at, say, the number 10, and then whatever G to the 10 is, then that's my commitment. I say, okay, now I'm committed to that polynomial. Okay. Now let's say this polynomial, I don't know how, but like let's go back to like rock, paper, scissors. And so like for rock, I have some polynomial, and for scissors, I have another polynomial or something like that. It's kind of weird to think of what the polynomials would be or why you would use polynomials in that case. Could I make my polynomial equal? Could I have it like a polynomial for rock and one for paper and one for scissors, but the evaluation of all those polynomials at the number 10 is the same? Okay, so I could choose a polynomial where they all intersect at the value 10. Okay, then they would all have the same commitment, and then when I go to open it, I can open it up to whichever one I want. Okay, so we can't just pick a value here and just say that you evaluate the polynomial at this point. Okay, another option we could do is we could pick a bunch of points. Okay, so I could, if I'm committing to a polynomial that's degree 10, I could pick 11 points and commit to those 11 points, and then I would be locked into that polynomial. I would have a commitment to that polynomial, but I would have 11 commitments. My polynomial would be 11 commitments big. Okay. Another option is I could just commit to the coefficients one by one. Again, I would have 11 coefficients for degree 10. Okay. So to commit to a polynomial, we have two options. We can commit to the set of points. And so we're going to end up with d plus 1 commitment values. We could commit to a set of coefficients. Then we would have d plus 1 commitment values. Okay, so by commitments, you're doing it d plus 1 times, and the number of values c here would be d plus 1. Okay. What I'd really like to do is I want to commit to the whole polynomial in one shot and just have a single value come out and say this single value commits to the whole polynomial. Okay. Now that seems a little bit crazy because this could be 1,000,000 or 1,000,000,000, right? And so I have this huge thing, and yet I want to come up with just one value c, right? And somehow that's going to have to lock in exactly what that polynomial is, so that if I have to open it later, I can't open it up to some other polynomial that it's not. Okay. So my wish list is to basically just have one commitment. Okay? And that's what we're going to do. Okay? So I'm going to show you a polynomial commitment scheme where you can have a polynomial, it can be very large, and what you're going to do is you're just going to, when you commit to it, you're just going to commit, you're going to have a single value that comes out. Okay? And so the name we use for this is succinct. Okay. And so I'm going to have a succinct commitment to a polynomial. Now, there's actually a very easy way of doing this if you know cryptography. You know what a hash function is. You could just hash them all together, and then you have g to the hash of all the coefficients or all the points. Now you have a single value. And if I want to open it up to a different polynomial, I would have to find another thing that hashes the same value. And a hash function is designed so that that's not possible. Okay, it's collision resistant. Okay, so getting a polynomial that's succinct is not that challenging, but it's something that we want to do. And the other thing I want on my wish list is why that hashing trick isn't going to work for us is when I open a commitment, generally I open up the entire polynomial. If I have a message, I'm going to open up the entire message. If I'm committing to a polynomial, I'll open the entire polynomial. But what I want to do is I want to have like a selective open, where instead of saying I reveal P, I want a protocol, so I will be able to do that as well if I want to, but I also want a protocol where I can reveal P of, say, alpha, okay, for any value that I choose. Okay, so this can be any value I choose. And so instead of telling you the whole polynomial, I'll just tell you what that polynomial is at the point 5. Okay, and you'll learn what that polynomial is at point 5, and you won't learn anything else about the polynomial. Okay, so this is kind of selective or minimal disclosure. And for polynomials specifically, we say we open at point. So I have a way of opening the polynomial, the commitment to the polynomial, but I can also just open the polynomial at that one point. And so you'll only learn what it is at that one point. Okay? And in order to do this, I'm not going to be able to just like give you a value and then you do it. Okay? We're going to have to engage in a kind of protocol. So we're going to go back and forth, okay? And I'm going to convince you that this value is correct, okay? So envision kind of like a protocol where I'm sort of proving to you that the polynomial opens at this point. But then when you take all the math in the crypto that we do and collapse it down, at least there's different ways of doing polynomial commitments. So some of them maintain an interactive. The exact algorithm we'll look at, it's called KZG. In that case, it just collapses down to just giving you a single value. So basically, to open it, I'll just give you a single value. You're going to plug that into an equation. You're going to check something, and then you're going to be happy that I opened the polynomial at that particular point. Okay? So because of this selective opening, I can't do the simple trick of just hashing all of this together. I need to keep some structure here. Okay? So I still don't know what the answer is. I don't know how I'm going to commit to this because I can't commit to it now because I have symbols or slots for a value. I don't have full numbers here, okay? And if I use hash functions, I'm not going to get this selective opening thing, okay? I'm going to tell you what the answer is in 2 words, but I'm going to show it to you next week, okay? The answer is somehow somebody's going to pick a random value tau that no one on Earth knows, okay? And when I commit to the polynomial, what I'm going to do somehow, even though I don't know the value tau, I'm going to somehow be able to plug the value tau in, and I'm going to get a commitment to my polynomial evaluated at this value tau. Okay? So my commitment to a polynomial is it's g to the power of what my polynomial is evaluated at tau. Okay? But I don't know what tau is myself. Okay, so I don't know what it is, and nobody on Earth knows what it is. Even the person choosing it. Yep. So this sounds impossible. It should sound impossible. Okay. And next week we'll talk about how that happens and why and why it works and all of those types of things. Okay. So I'll see you all next week. Yep. Go